Welcome back to the lecture series on data structures. In this lecture, we talk about binary heaps. A binary heap is a special binary tree, which is complete binary tree, and it can be implemented in two ways, either a max type of heap or a min type of heap. In the case of max heaps, at every node, the value of the parent node is greater than or equal to the values of the children is to be followed. Whereas in case of min heaps, the value of the parent should always be less than or equal to the values of the children. So if we follow any one of these conditions, either it becomes a max heap or min heap. When it comes to the operations on binary heaps, the first operation is insertion. Given a binary heap, if we want to insert an element into the heap, we will add it as the last element of the binary heap. By insertion of the element as the last node, it may or may not satisfy the conditions of heap, either max heap or min heap correspondingly. Then we need to restore the heap condition through set of operations. Similarly, when it comes to the deletion, we delete the root element. If we want to delete the root element, first we swap the root element with the last element and then delete the root. But because of this operation, again heap condition may be lost. So to restore the heap condition, we need to readjust the nodes. That is in case of deletion. Of course, even if it is not a root node, if you want to delete a parent node, the same scenario has to be applied. That node has to be replaced with the last node and then delete the last node and readjust the nodes so that they restore the heap conditions. In this process, there are two types of heapification. We call it as heapification, heapify up and heapify down. That means when it comes to the heapify down, this operation is used after deletion of a node to move down the last node which is replaced with the root node to its location. That is called heapify down. Similarly, heapify up is used when a node is added at the end and gradually it has to move up to find its corresponding location. So these are some of the operations that we perform on binary heaps. Now here are some examples of heap. The first one is a max heap where the greatest element is at the root node and all the remaining elements are less than that. 50 and 70 are the children of 80 which are less than 80. Similarly 20 and 30 are children of 50 which are less than 50. Similarly, in case of min heap, the parent node should be less than the children node in this case. So the root node is the least element of the rest of the elements in min heap, and 2 is less than 5 and 20. 10 and 15 are greater than 5. Of course, 5 is less than them, and 20 is less than 30 and 40. So this is min heap. Now, when it comes to the implementation, operations on min heap and max heap, there are two types of operations. One is array type of implementation, another is linked list implementation. When it comes to the array type of implementation, usually array may consist of n number of elements. Starting array index may start from 0 to n minus 1, but we can also maintain the level order index of the nodes. Here in the example, you can observe the level order indices of the nodes. The advantage of array implementation here is the binary heap being a complete binary tree. Given n number of elements, there are no gaps in between 1 to n for the level order index, so that they form a complete set among themselves. So array implementation is more advantageous when it comes to the heap implementations for smaller ones. Given an array, here the question is how do we identify the parent, right? Here the level order index is useful for us. If I is the level order index, if you remember, 2 times of I is the left child and 2 times of I plus 1 is the right child given I. So based on this information, we can calculate for the children as well as parents for any given node. For example, if I take 5 and if I want to identify the parent of that node, 5 by 2, floor of that 5 by 2 should give me the parent. So here 3 and 4 are the children of 1 and 5 is child of 2. This is how we can identify the child and parent relationship in an array. Insertion of a value into the heap is the first operation that we perform here. We'll observe that. given an array, the input is the array to be inserted, and level or maximum level order index, that is the maximum number that is present in case of level order index, and the value to be inserted. Here the purpose of max level order index is, it being a complete binary tree, the array size may be larger, but all the elements may not be filled. So what is the current location to which the array is filled is identified with the max level order index. And in the insertion part, if you remember in the previous slide, the node will be inserted as the last node. So we need to identify what is the maximum level order index, and we need to add the new element as the next one. So for that purpose, we need max level order index. Now, if max level order index is 0, that means array is completely empty and no binary tree is there or heap is there. In such case, the first node itself should be added there. So a of 0 is equal to val, and max level order index is updated as 1 and exit. So first node is added in the heap. Else, that means already heap is there. Then since we know the max level order index, that's the last element, we need to add the new element as the next element of that. We update max level order index is equal to max level order index plus 1, and in that location we keep that value in the array. So a of max level order index minus 1 is equal to val. So why we have taken minus 1 is the array index is running from 0 to n minus 1, whereas max level order index runs from 1 to n. So that is why we are taking a of max level order index minus 1 as well. And once we add the value, is added as the last node, fine. But addition of this may violate the conditions of the heap. We need to move this element to its corresponding location that satisfies the heap conditions. So for this purpose, by taking I as an index for max level order index, and we are heapifying up. How do we do this? We do this while I greater than 1, as long as I is greater than 1, parent index is identified. So when new node is added at the last, we need to check whether this is less than the parent value or not. So we need to identify the parent node. What is the parent node? Floor of I by 2. Floor of I by 2 gives us the parent value. Parent index is equal to floor of I by 2, and at that location, if a of parent index minus 1 is less than a of minus 1, the heap condition is not satisfied. Then swap them. Swap a of parent index minus 1 comma a of minus 1. If it is not the case, just simply follow the while loop. So once we swap, I is updated as parent index. That means the value has moved up, and this has to be continued until while condition is violated. That means I greater than 1. That means we need to check until the root node whether the existing node that is added to the tree reaches its corresponding position or not. Here is an example. 80, 50, 70, 20, 30 are the values, and you can observe the binary tree also, it being a complete binary tree. And then if we add a node 90 at the end, if we want to add the node 90 at the end, that becomes the 6th level order index. We need to add it as a last element. So the last element being 6, that is added as the left child of parent 3, 70. Now once we add this, next we need to heapify up. How do we heapify up that? We compare with the parent. 90 is compared with 70. So 70 is less than 90. So we need to swap these 90 and 70, and parent index is updated. This 90 is greater than 80. It's parent. Again, we need to move this 90 up to its swap by swapping with 80. So 90 has reached its position. This is how we insert a node into the heap. In the previous slide, we look into the insertion of a value into the heap in the form of an array, when the heap is in the form of an array. The same thing can also be implemented using linked lists. So the same scenario here, instead of adding a value to the array, adding a node as a leaf node, and then we heapify up that value of the leaf node to its corresponding location. So same logic is used, but only thing is instead of using arrays, we have used linked lists here, double linked lists here. So insertion, again heap, max level order index and value are same. If max level order index is 0, that means no value is there until such time, then here we need to create a node. Heap is equal to create node, data of heap is equal to val, and now max level order index is also stored in the node. Along with the data, here in the node we also store the max level order index. Max level order index is 1, and left child of heap is null and right child of heap is null, so exit. Else, if that is not the case, that means already it is existing, then I is equal to max level order index plus 1, it is updated, and parent index is equal to floor of I by 2, and parent node is identified. So parent node is identified through a program or a algorithm, search heap for the parent index. Once we identify the node, then starting from the root node, we keep on searching until we come across that parent node. Once that node is identified, again if left child is null, then we need to create a node and add it there. Or if left child is not null and right child is null, we need to identify that and we add it to the right child. Once this is done, that is added as the last element, then we heapify up here. Again the same logic applies. While I greater than 1 and parent index is identified, and parent is equal to search of heap, then temp1 is equal to search of heap, that is taken into temp1, and data is swapped. Actually data is swapped with respect to the parent and the child node. Then this swapping is done until it reaches its location. So in the while loop it continues until I greater than 1. When it comes to the deletion of a node, we start with the heap, max level order index, and val as an input. The value to be deleted is to be identified in the index. So I is equal to 0 while a of I not equal to val, I is equal to I plus 1. So we search through the array until we identify the value to be deleted from the heap. Once that is identified, the corresponding max level order index is identified, level order index is equal to I plus 1, and then we need to swap the last value with the node to be deleted. So swap a of I and a of max level order index minus 1, the last element. So once we're swapped, then we can make this a of max level order index minus 1 as null. That means element is removed, but we need to heapify down. So heapify down the subtree after the swap, while 2i is less than max level order index and 2i plus 1 is less than max level order index. That means we are comparing the max level order index with the children until it is greater than them. Left child index is equal to 2i and right child index is updated. If a of left child index minus 1 is greater than a of I, we need to swap them. Else I is equal to, of course, swap a of left child of index minus 1 comma a of I is equal to left child index is updated as lower one. Else if a of right child index is greater than a of I, in this case we are talking about max heap, so parent node cannot be less than the child node. So if it is the case, we swap them again, swap a of right child index minus 1 comma a of I and update I as right child index. So this process is continued until we reach the corresponding location. So this is called heapify down. In essence, for deletion, what we are doing is we are swapping the element with the last element and then we are heapifying down so that after swap the element reaches its corresponding location.